So we start again with the last talk of today. So the speaker is Tim Tait from University of California, Irvine. His talk is about an early period of QCD confinement. So please, Tim, go ahead.
Thank you very much. Sorry, I had to stop sharing for a moment so I could see where to unmute myself. So it's very nice to be connected today. It's a little bit in the morning in California. And this talk is going to be a little bit different than the ones that have already taken place this week, though it actually does connect back with sort of the unique role that the LHC can play for teaching us something actually about the early universe. And so there's some aspects of cosmology, of QCD, and ultimately of LHC physics represented here. So like I said, it's very nice to be connected. It's a pity I'm not actually there in Italy. For those of you who speak Italian, mi dispiace tanto che non sono là con voi. So let me get started. Also, I should mention, I'm not going to need an hour and a half. So unless there's a lot of discussion, which of course I hope there will be, this may end a little bit earlier. So what I'm going to talk about is a theory of physics beyond the standard model that is sort of uniquely suited to be probed at the Large Hadron Collider, but it tells us information that is not exactly the one that we typically think of the LHC providing. And so I find it an interesting line of work for that reason. So here's an outline of what I'm going to talk about today. The motivation is actually exploring novel cosmologies, just asking, what do we know about the early universe? Where is there room that things could be drastically different than actually what we think they might be? And the one in particular I'm going to focus on is an early period of QCD confinement. So the idea that actually the strong force had a different coupling at early times in the universe's history and actually confined at early times, which is very different than the picture that is standard, where we think that QCD, of course, is confined today. All of the quarks and gluons are frozen into hadrons. But we think at early times of the universe's history, actually at high temperatures, QCD goes through a phase transition, it deconfines, and so we describe the early universe as a plasma of hot gluons and quarks. This actually idea, it turns out, might explain some of the mysteries, or at least shed light on some of the mysteries of cosmological observation. And I'll say a little bit about all of those, actually, since they're kind of the primary motivation, and they identified parameter spaces interesting that we would like to be able to probe. And these include generating the matter-antimatter asymmetry, right, or the baryon asymmetry that we observe in our universe. It can say something about how dark matter freezes out and the abundance of dark matter in the universe today. And also kind of alternatively, because either you can have a WIMP dark matter freezing out, or another option would be to have axions make up the dark matter that solve the strong CP problem. And it turns out this also might have a big impact on Axion production. So I'll say a few words about both of those things. And then I'll finish up by talking about its signals at the LHC and other future colliders, which as far as I can tell right now, are very close to the only way that you could actually tell that something like this was going on. And then I'll finish up with some outlook. So first, some introduction. The invitation to this talk, in some sense, is just asking, what do we know about the universe? And so what I've written here is an axis where I have temperatures written. The temperatures are decreasing, and that the idea is that as the universe is expanding, it's cooling down, and therefore, we have temperatures we think that probably were as high as 100 GeV or even higher, perhaps. And the universe cools down through the GeV, MeV, and EV scales. Of course, particle physics knows quite a bit about all of these scales. And so just using the ingredients of the standard model, we know that about 100 GeV, we expected there to have been an electroweak phase transition, where we went from having no expectation value to the Higgs to having an expectation value, and therefore fundamental masses turning on. And around the GeV scale, the QCD phase transition takes place. And that was the one I mentioned before, where the quarks and gluons give way to the mesons and baryons. Now, in BSM physics, we also think that these scales may be quite interesting. So for example, at around 100 GeV, many theories of electroweak baryogenesis produce the asymmetry between matter and antimatter, which in this case is an asymmetry between quarks and antiquarks. Though, of course, this is less certain, since we don't know for sure that electroweak baryogenesis is actually the correct theory of matter-antimatter generation. At maybe temperatures around 10 GeV or so, and this depends somewhat on the mass, so this is a rough scale, we think that the WIMP dark matter would have frozen out. And so it may be that something interesting was happening also in the universe around that time. And again, we're not sure that the dark matter is WIMPs, we're not sure what mass it has, and we're not sure that freeze out was the mechanism that produced it. So this is also an uncertain scale. And then finally, in the yellow, I have written things that are related to our observations. And so of course, we live today at very low temperatures. Around EV, we have a very good understanding of what the universe was doing because of the cosmic microwave background observations. And going back to around MEV, Big Bang nucleosynthesis, right, which predicts the abundances of the light elements, is also pretty well understood and is a pretty clear indication that we have a decent understanding of the universe at temperatures down to MEV. And the whole point of the talk essentially is the observation that at earlier times, so at temperatures higher than MEV, we really don't have observational probes that are helping us understand what the universe looked like. In fact, in some sense, the only measurements we really have from those times are the inputs into these things. So for example, we know there is a matter-antimatter asymmetry, right? So that tells us something about the universe, but it's really very vague and doesn't specify what the theory is. And similarly, we know there is dark matter, and therefore, so there must be something added to the standard model, but again, we're not sure what that is. So all of our understanding theoretically of what the universe looks like at times before BBN is really just by taking the boundary conditions at BBN that we understand, taking the contents of the standard model, plus some important things like the fact that there is dark matter, and then just treating this like a movie that we can run backwards using the laws of physics. So basically everything earlier than BBN is an extrapolation. And that means that we don't really know what we're doing, and it would be very important to explore other possibilities. So what I'm going to do is I'm going to explore the idea that the QCD phase transition, instead of happening at the GeV scale, happened at a much higher scale. And so I'm going to be modifying this early time where there is not much data, but in a way to try to understand what it has to say about these other things like baryogenesis and dark matter. So, in the ancient cartographers, when they didn't know what to put on the map, they put a dragon and said, here there be dragons, so here there be dragons. And of course, it's also unfortunate, but I should note that this year we are dealing, like last year, with a dragon of a different kind, though there are some signs that we are learning how to deal with it at least. So if we're hoping to learn about fundamental physics from early cosmological probes like the abundances of dark matter or baryons, then of course knowledge of the cosmological history of the universe is essential. And a non-standard picture, even at early times, could really distort how we interpret these observations. We have a lot of ideas for what dark matter could be, for example, and they're all informed by the fact that we think that we need to explain its abundance, and we have a standard picture for what the universe looks like, which allows us to do this calculation. But if the universe were different, the calculation is different, and the dark matter parameter space is different, and we're going to see an example of that. So I would argue we need to have some understanding of the space of the possible universes that we could have at early times to put these into context. So the one in particular I'm exploring is a very old idea, actually. It's the idea that the coupling constants, which of course in quotation marks, because we've known for now about 100 years that these coupling constants are not actually constant. But the idea is these couplings could take very different values at early times is something that has been explored before. And of course, again, at late times, we have good measurements that tell us that if the couplings were changing, they were changing very slowly. But all of these probes happen at a later time than BBN. So really, we still don't know much about what happened to the couplings at early times. And so there's still room for us to play. Okay, so what I'm going to do is focus on what I consider a somewhat radical idea that QCD has a very different coupling at an early epoch that it actually confines at that time. So there's another confinement scale that's much larger than GeV. Of course, then the idea is as the universe cools, this QCD should eventually deconfine. It should go back to normal. It has to match the observations that we make today. So lambda QCD has to go down to its value. And those of you who are precision physicists, and I see that some of the people connected are going to perhaps be a little bit nauseated that I keep saying that lambda QCD is 1 GeV. Of course, I don't mean that literally. I just mean it's around a GeV. So you can replace that with whatever value you prefer for the number of flavors you'd like to work with, 300 MeV or whatever it is from your favorite set of PDFs. So when I say 1 GeV, I just really mean the standard model value. And then of course it has to relax back to something like the standard model. And one could have modest modifications that just change the coupling a little bit. And of course you might think, just in the interest of being conservative, that modest modifications are more likely than drastic ones. But I'm also trying to push things as hard as I can and actually see if I can break the universe, make the universe very different and not run afoul of any observations. And so I'm actually trying to be radical in some sense here, not because I think it's more likely, but just because I think that it's worth to see whether this is actually allowed or not. And I think, as we're going to see, it's fun to do this. So it's also interesting intellectually. And one can play similar games with other couplings, the standard model. So for example, the SU2 weak interaction, you could make it confined at early times before it eventually gets Higgsed. In that case, you get an even weirder universe than the one that I'm going to be describing, and you can read about it here. So you can see that I'm also working on something like that related to dark matter, and that the date for the archive that I had guessed was very, very wrong, as it turns out, but that's another effect of the pandemic. Okay, so let me describe what this looks like and what it means and how we describe it theoretically. So the idea, first of all, is that we introduce dynamics that promotes the strong coupling constant to be a dynamical field. So, and I have to apologize that on some of my slides, this is phi and some of it is S. It's just because I've written a couple papers with different collaborators. They like different notation. And that means some of the plots have either phi or S on it. So the idea is that we have the kinetic term for the gluons in the standard model. And as usual, you can normalize that such that the gauge coupling appears as a prefactor of that term, right? Of course, I can rescale my fields and then the coupling goes back to the interaction terms like normal. And the fact that I can do this universally is a consequence of gauge invariance. So what I've done is I've taken that usual term that would just specify the strong coupling constant, and I've added to it a dimension 5 operator that contains this new scalar field phi, and then there's some mass scale that characterizes the strength of phi's interaction with the gluon field strengths. So if you want, actually, this looks like the low energy effective field theory for which the Higgs interacts with the gluons. And in that case, there'd be a prefactor here that would contain the loops of top quarks. And that would determine what M star is. But in this case, phi is not the standard model Higgs. It's just some other standard model singlet field. So now when I do the rescaling and put the coupling back into its canonical form, the effective coupling I get is now a function of the vacuum expectation value of phi. And it depends on both this the constant that I chose, G0, and also the VEV of phi in the following way. And so you can see that actually, if the term in the denominator turns out to be negative, say because the VEV of phi is negative, then actually the coupling gets stronger. Otherwise, it gets weaker. And phi could be actually something like a dilaton or a radion in a theory with extra dimensions. They both have effective theory descriptions that look like this. It could also just be something more prosaic. It could just be some scalar field that couples to some kind of colored fermions, like vector-like quarks, and that induces radiatively a term like this too, at energies that are much smaller than the masses of these new fermions. And G0 is a strong coupling in the absence of a VEV, and it runs just like an ordinary QCD. So one loop, if I look at this running, then 1 over alpha effective is equal to the one loop running of the bare coupling that I wrote down, including the one loop beta function. And then the extra term at tree level, which is just modifying the value of the coupling. So now using the RGE, I can ask at what scale QCD gets strong. And I can write that scale as, so the scale in this theory in the presence of the phi VEV is always denoted as lambda, and lambda 0 corresponds to the scale I would have if the VEV were 0. So this scale is now modified, but it's modified exponentially because, of course, the value of lambda depends exponentially on the boundary condition for G strong. And so again, written out in terms of the number of flavors and the VEV of phi, I can see that actually I can get very different values for the confinement scale with even actually a fairly modest value of phi over M star. And in general, I'm going to parameterize this by saying that the lambda in the presence of phi is equal to the lambda in the absence of phi, and then times C, which is just a scaling factor that tells me how much stronger the confinement scale is than it would have been in normal QCD. If I have 6 flavors, as I do in the standard model, and I want to get a confinement scale around TeV, that tells me that I would need to have the shift in phi be over m star be something about minus 0.8 or so, which is largish, but it's actually small enough that it is still consistent with the effective field theory picture. And I mean, I'm using EFT just because it's convenient here. There's nothing really essential that says that the degrees of freedom I'm integrating out should actually be heavy. If I were inducing this radiatively, however, it would require a large number of vector-like quarks at m star, around 10 or so. Again, though, their masses would be multi-TeV. It's not clear that this is really a problem, though there would definitely be some spectacular things to see at the LHC eventually. And this plot just shows as a function of temperature. So now the temperature is increasing on the axis. So time would be going from the right to the left. And you can see that with no VEV, right, the strong coupling is blowing up around a GeV or so. And then as I turn on VEVs, you can see that confinement happens at an earlier time, like maybe around 20 GeV or even like 500 GeV. So all of this magic has got to be induced by a potential for phi. I need this potential to receive temperature-dependent corrections such that phi actually makes the shift that I'm talking about, starting looking different at high energy, at high temperatures, and then looking like the standard QCD value at the low temperatures. So, what I have in mind is a picture something like initially there is some value for phi that corresponds to lambda QCD being a TeV. So around TeV temperatures, we're confined. And so we have some high period of confinement, but then because the potential for phi has temperature dependent corrections, as I move from high temperatures to low temperatures, the VEV of phi shifts to another value. This changes the value of lambda QCD down to around GeV. So when that happens, the theory deconfines, right? Initially, I actually go back to a description of quarks and gluons, but then of course, as the temperature continues to fall, eventually we get to temperatures of order GeV, at which point QCD confines once again. And at that point, theory looks very standard, like the standard model. So we have to have a potential for phi that does these things. And you can imagine there's actually many different ways that you could obtain an appropriate potential. So for example, you could imagine that there are some new fields, maybe they're fermions, call them psi just to be generic, with sort of order 1 couplings to phi and masses around the TeV scale. When the temperature is around their masses, their corrections become exponentially suppressed. So at high temperatures, they restore the symmetry in the phi potential in the usual way. We would expect the phi VEV to be around 0. But as the temperature falls below their masses, the underlying potential for phi that might look more like a Mexican hat, like the Higgs potential in the standard model, becomes visible because their corrections become irrelevant. And then at that point, we could shift to another VEV for phi that corresponds to the standard model value. Now, since phi is a standard model singlet, these new fermions psi, they don't have to be SU3 charged or electroweak charged. LHC bounds on them are very weak, actually, and they could even have masses down around a few hundred GeV and be difficult to probe. They might be the dark matter, and that's something I'll come back and explore at the end of the talk. So, this is one picture for how you might do this. But of course, as much as I'm saying they're not very easy to probe, they are actually very important for the properties of phi itself. If they're light enough, phi could decay into them. So therefore, it might have missing energy signatures. And so, they might play an important role in its decays, etc. So they're not unimportant. It's just that they're not that easy to probe. Another option would actually to make use of the fact that phi is a singlet, and it therefore has inevitably cross interactions between the standard model Higgs and itself. So I apologize, this is now where I switch notations. So what I was calling phi is now S. You can imagine there's some potential for the standard model Higgs. It looks very standard. There's a potential for phi right now, S, which is just some polynomial in it. So I've just written down kind of a generic normalizable potential this way. And then there's some potential that includes terms where phi interacts with either h squared or phi squared interacts with h squared, right? So these are also both normalizable interactions between the standard model Higgs and phi itself. And the whole point is that around 100 GeV, the Higgs goes through a switch where its VEV turns on, and we could use that switch to actually trigger either confinement or deconfinement in this theory. So this, of course, is a pretty complicated model in the sense that in addition to the sort of 2 standard model-like parameters, there are 4 parameters in the phi potential, and two parameters that describe the cross interactions between phi and h. So it's somewhat complicated to analyze what happens cosmologically, but what we find is that there are parameter points where one can actually realize the cosmology that I'm interested in. So at some point there is a high value, so sorry, this diagram here in the center of the plot is actually the VEV of S versus the VEV of the Higgs, right? So this describes what the vacuum is doing at any given time. So at early times, there's a VEV for S, which means that the value of the QCD coupling is modified, but we're at high enough temperature that there's no VEV for the Higgs. And so things kind of evolve in a fairly constant way until the VEV for the Higgs turns on. And at that point, it changes the potential that phi sees, and it actually transitions to a new value. But this new value may not be stable, and it may eventually roll down to a point where the VEV for S has become 0, and the VEV for the Higgs is actually turned on to the standard model value. And so we've actually done some, not really scans, but we've found parameter points to prove that this can work. These plots here at the bottom are actually showing you what the combined potential for both the Higgs and the singlet phi are. So really, these are the same as that plot in the middle. And it's just got contours of the potential shown. And so for a certain set of parameters here on the left at high temperatures of 200 GeV, we actually have two minima, both a global one here at a large value for the phi VEV and 0 value for the Higgs VEV. And then there's also a local minimum, which is occurring actually for 0 VEVs of both of them. Then taking the same parameters and evolving down to around what the confinement scale would be in this case, which turns out to be 85 GeV for these parameters. So it's not quite a TeV, but it's close. Then we see actually the potential has evolved such that we now have the global minimum occurring more or less where we want it. The local minimum is actually moved a little bit as well. So these two have sort of changed their relative position to each other. And so at this point, though, we're still at a position where we've rolled from where we started at the red point on the left. Now we're close actually to the blue point in the middle. But as we go to even lower temperatures, this false minimum continues to rise, the true minimum continues to fall, and we get to a position where the actual global minimum is right where we want it for low temperatures at a non-zero value for the Higgs VEV, but a 0 value for the phi VEV. And so this continues, the universe continues to roll down to the bottom of this, I guess it's like a valley or something. It's kind of like a bowl or a depression until you get to the point that looks standard model-like. So for these parameters, we start where we want and we end where we want, and we kind of go through an interesting history where we roll down to get there. So it's interesting to talk about what happens during the first QCD phase transition, the high scale phase transition. So the first one takes place at high temperatures before the electroweak symmetry breaks, and therefore it has massless standard model quarks. If there are 6 massless flavors, this is expected to be a first order phase transition based on some very old arguments from Pisarsky and Wilczek. And that means that the combined vacuum forms via bubble nucleation. It's different from the QCD phase transition that we have in the standard model, which is a crossover. It's actually a violent transition where vacua of the new phase form, and then these bubbles actually grow until they fill up the whole universe. So after confinement, the chiral symmetry breaking also breaks the electroweak symmetry, and the condensate of the quarks, the chiral condensate, acts as a tadpole for the Higgs and induces a VEV for it. So in some ways, this is actually what I would call old school Technicolor. There's something going on that looks kind of like Technicolor dynamics, but it's happening in the early universe, and it's actually QCD and not some exotic confining theory. This diagram is just a phase diagram from QCD that I took from this review. It's not actually really relevant for what I'm doing here, but just to remind you of what the phase diagram looks like in ordinary QCD as a function of the masses of the up and down and the strange quarks. The physical point is here in the crossover region. And the point is that if we go to all of the quarks being massless, we're back in the first order phase transition. So this is actually another indication of that argument of Pisarsky and Wilczek. Of course, our theory has 6 flavors and not 3, so it is different. So here's a cartoon of what happens at the high scale confinement temperature. Then we had quarks and gluons in the plasma. They were all streaming around. Out here, there's no chiral condensate. There's no Higgs Bev because the temperature is higher than the electroweak phase transition. And then we nucleate a bubble of the vacuum for this temperature, which has confinement. So inside this bubble, the quarks and gluons are confined into hadrons. The QQ bar condensate is of order lambda cubed. And as a result, the Higgs Bev is actually turned on. And I'll describe all of this mathematically, but this is just a kind of a guide for what the next slides say. In the confined phase, the important active degrees of freedom are actually the 35 pseudo-Nambu-Goldstone boson mesons, right? 35 because there are 6 massless flavors at that time. Their properties are described by chiral perturbation theory. The parameters have to be matched to low energy QCD data, and the dimensional quantities are scaled up to the high scale confinement scale. So the quantities that we normally see inside the chiral Lagrangian, so kappa is the coefficient of the term that becomes the pion masses. That's actually this equation down at the bottom. F pi and M pi, right, which is a function of the other two, are all scaled up by an appropriate power of Xi. And so you can see that overall, the masses of the pions squared look like the masses of the pions in the standard model squared times Xi, so they grow, of course, and then also times the ratio of the Higgs Bev at this time to the Higgs Bev at 0 temperatures, the Higgs Bev that we know. And so we can actually compute the spectrum of mesons. Here's one particular example where the confinement scale was set to be around TeV. Sorry, it's either set to 500 GeV or a TeV. That's the blue and the green histograms. And you can see that we have mesons as heavy as around a TeV, and as in, very close to massless, though still much heavier than the mesons of the standard model. The point I was making about the tadpole for the Higgs can be seen from this term in the chiral Lagrangian, right? So in the chiral Lagrangian, we're used to thinking about this as just an interaction of the pions themselves that comes about from the fact that the masses break the chiral symmetry. In this case, though, because the mass term contains the Higgs, and the Higgs is still a dynamical degree of freedom at 1 TeV, this actually turns into a tadpole term for the Higgs, which is dominated by the top quark. And so the fact that there's a QQ bar condensate, right? If that happens when that happens in the ordinary QCD at a few hundred MeV, the top quark's irrelevant. The effect on the Higgs is irrelevant. When it happens at a TeV, the top quark is light, and the effect on the Higgs is actually quite dramatic because the top is an active player. There's actually a TT bar condensate along with everything else. And this plot actually shows as a function of temperature, right? So again, you imagine that time starts here on the right and goes to the left. For different values of the early confinement scale, what the Higgs Bev is doing. And you can see that actually, if you scale up the early confinement scale to a TeV, you actually go through a period where the Higgs Bev is much larger than in the standard model. There's a period of the universe where the Higgs Bev is 500 GeV or so. And then eventually, of course, it falls down to its normal value when things start to go back to normal and deconfinement. And it's less dramatic if you have a smaller scale, but still actually there's a larger Higgs Bev at some time. And that's relevant for computing the pion masses. So let me say a little bit about how this theory produces spontaneous variogenesis. Famously, of course, the standard model does not have a sufficient CP violation in the CKM phase to generate a baryon asymmetry that's as big as the one that we see. There's a very interesting and actually very old idea from the 90s to try to use a strong CP phase as the source of CP violation. So the idea is you write down, a usual theta term for the gluons. Theta, of course, can be related to some raw theta term and also the phases in the quark mass matrix. And the idea is that this phase is actually a source of CP violation that could also drive variogenesis. Now, observationally, of course, there's a problem with that because observationally, we know that this phase is less than 10 to the minus 10. It's far less relevant even than the CKM phase is. However, the idea is that if there's a dynamical solution to the strong CP problem like the axion, the effective phase could be very different in the early universe before the axion reaches the minimum of its potential. So this is still another example of an idea that I'm exploring where the universe is different, it has different properties at early times. And in this case, not only am I imagining that I modify the strength of a strong coupling, I'm also thinking that the axion is a theory where naturally I modify the value of the theta term. So there could be actually a lot of CP violation in the early universe before the axion reaches its minimum, which cancels theta bar. So the axion is another example of this kind of theory. And the rolling of the axion to its minimum also provides an out of equilibrium condition that's necessary to produce a net baryon asymmetry. And that was explored by these authors in the 90s. So the challenge that they faced was the fact that there's a mismatch in the scales. Baryogenesis requires both the out of equilibrium condition and also that for there to be baryon number violating processes. The standard model has baryon number violating processes in the form of the electroweak sphalerons, but these switch off at the electroweak scale. So they're only active at very high temperatures bigger than T electroweak. However, the axion only starts rolling to its minimum at the QCD scale. And so there's no out of equilibrium condition when the sphalerons are active, and there are no sphalerons when the out of equilibrium condition is active. And so that tells you that this theory has difficulty generating a baryon asymmetry. Now, these authors actually address this challenge by invoking a supercooled electric phase transition. This was also picked up by Geraldine Servant and Benedict von Harling, who looked at this in the context of Randall-Sundrum type theories. And so there are ways to solve actually this problem. And what they typically do is they move the electroweak transition down to where the QCD transition takes place. What I'm doing is obviously the opposite. What I'm going to imagine is that the QCD phase transition takes place here above the electroweak phase transition. That means the out of equilibrium condition is now happening at the time when the sphalerons are actively violating baryon number. And so all the conditions to generate a baryon asymmetry are actually satisfied at the same time. And so I can very quickly sketch what the calculation looks like. It's a little bit technical, so I'll actually go a little fast and you can ask me questions if you want. But the idea is that the non-zero theta effective we have at the time of confinement looks actually like a tadpole for GG dual. So the VEV of GG dual is related to the effective theta at that time, and also to the parameters of the axion potential. So that's why there's an FA squared times MA squared. But GG dual is actually a source for WW dual, the CP violation in the SU2 sector. And one way you could understand this is that if you imagine a particle like the eta prime, it couples through, it has a CP odd and it couples to both GG dual and WW dual. And so there are actually terms in the Lagrangian that connect GG dual to WW dual through the exchange of something like an eta prime. Now, at the time that I'm talking about, it's sort of when confinement is happening. And so it's not clear the eta prime is really a good degree of freedom. But you can imagine that instead, when I write eta prime, what I mean is a certain CP violating combination of a quark loop going on in here. So that looks like an effective Lagrangian that includes the properties of the eta prime and couples GG dual to WW dual. But now because GG dual has got a VEV, we can replace that by its VEV in this equation. And so this actually just looks like a tadpole for WW dual. But remember that through the anomaly, WW dual is related to the divergence of the baryon current. So I can replace WW dual with the baryon current's divergence. This whole thing here that depends on what theta effective was and the axion parameters and the eta prime parameters, I'm just going to call some susceptibility chi. And of course, it's a function of temperature because all these other things are a function of temperature too, in particular the axion masses. And if I integrate by parts, then this actually looks like a chemical potential for the baryons. So integrating by parts, the effective baryon potential, the baryon chemical potential, is the derivative of chi with respect to T. I can plug in what I have defined chi as, take the derivative, and then that leads to a production for that leads to a prediction for the baryon production in terms of the sphaleron rate and this effective chemical potential. So I can plug all of these things in. I can plug in the temperature dependence of the axion mass. I can plug in the temperature dependence of the sphaleron rate. Remember, this is all happening before really SU2 is broken, and so the sphaleron rate is unsuppressed. And the resulting baryon asymmetry I get parametrically looks like this. It's 10 to the minus 11, the sine of the initial theta angle, then the Higgs VEV at that time divided by lambda QCD at that time, and then T sphaleron cubed over T reheat cubed. And T sphaleron is the temperature at which the sphalerons turn off, so it's the electroweak scale. And T reheat is the reheat temperature, which allows for the possibility of additional entropy production during the phase transition. Since the electric symmetry is strongly broken during the confined phase, as long as the deconfinement temperature is below the usual electroweak transition, so the sphalerons never switch back on, we expect that the sphalerons and the reheat temperatures are similar in magnitude, and so this factor is of order 1. And in fact, I'm looking at the whole thing and remembering that in order to explain the universe we see around us, we need a baryon asymmetry of around 10 to the minus 10. This is really in the right ballpark, actually, provided this angle is fairly close to maximal, and the Higgs VEV is a bit bigger than lambda QCD, which we saw is actually something we can obtain for reasonable choices of parameter space. So there's actually not even a huge dependence on any of the free parameters. Most of the stuff is kind of canceled out. None of the Axion potential parameters are left behind. And that's because MA squared times FA squared is basically just M pion squared. So we have a prediction that we produce baryons, which is very close to the one that we actually expect. So that's basically just a nice idea that, why would I bother with this whole thing with early confinement of QCD? Well, I can do that to explain the matter-antimatter asymmetry of the universe. So let me quickly say something about WIMP freeze out. We can imagine also that, and I have to say, this is really completely, in some sense, a side thing to generating the baryon asymmetry. I could make these models coexist, or I could just say, well, maybe I don't want to explain the baryon asymmetry this way. I can still actually say something interesting about dark matter freeze out, just using early confinement as well. So I'm not going to really make much reference back to the baryon asymmetry when I talk about the dark matter freeze out. What I am going to imagine is that there's some WIMP-like particle, which is a standard model singlet. It's a Dirac fermion that likes to interact with quarks. So for example, I could imagine writing down some interaction between chi bar, that's the dark matter, and QQ bar. And of course, the Qs have flavor indices, and so in principle, these couplings are flavor couplings. In practice, what I'm going to do is I'm going to align them with Yukawa couplings. So basically, chi bar will couple to UU bar or DD bar or SS bar, so forth, TT bar, but I'm not going to actually allow them to have flavor violating couplings because those are very highly constrained by flavor observables. And if I'm imagining by writing this as a dimension 6 operator that the mediators, whatever it is that mediates this interaction, is heavy compared to the energies of interest, or heavy compared to the mass of chi, really is what matters. And I just assumed for now that this was a scalar interaction and that its flavor structure is minimal flavor violating. So that's again to avoid those constraints from flavor violation. So if the singlet field phi is heavy and has some mixing with the Higgs, it would actually induce an interaction just like this one. So you can imagine that actually the mediator is my phi particle itself. So if I imagine that the dark matter freeze out is happening during the time of early confinement, the right degrees of freedom are not the quarks, they are the mesons. So I have to take my interaction and use chiral perturbation theory to figure out what it implies for the dark matter interacting with mesons. So again, there is this same parameter kappa that describes the low energy effective theory for chiral perturbation theory. There are the fermions, and then there are some terms that involve both the interactions and also the exponential of the pions. If I expand this actual U field out into the pions, I end up with a term that actually just looks like a correction to the mass of the dark matter. So in other words, early confinement shifts the mass of the dark matter to a new value. And then there are also terms that look like two dark matter particles interacting with two pions. So, so what I have is some interesting thing. I'm saying that if the dark matter freezes out during the time of early confinement, its mass will be shifted away from the value that it takes today at zero temperature in normal QCD, and also its interactions will be with pions, and these interactions are actually enhanced because if you remember, kappa goes like lambda cubed, f pi goes like lambda. So actually these interactions overall grow with that scaling factor c. And so here I have written down how much the shift in the mass would be. It's also actually cute to say that, if this were ordinary QCD, it would still shift the mass of the dark matter. It's just that ordinary QCD lambda is so small that for a WIMP, you wouldn't actually think that mattered very much. So from here, we can do a standard freeze-out calculation and ask what the abundance of dark matter that we get is. So for example, we can calculate the cross-section as a function of the dark matter mass. And this is the dark matter mass at t equals 0. Remember, at confinement, the mass is slightly shifted. And so the different plots show you solid lines which have C = 1. So this is the standard case where the dark matter is freezing out into quarks. You can see, because I have a scalar interaction, as the dark matter mass crosses the TT bar threshold, there's a big enhancement, because I assume that the coupling scaled with the Yukawa couplings, and so therefore it couples much more strongly to the top quark than it does to other quarks. And in this plot here in the upper left, the different colors just refer to different values of that interaction strength between the dark matter and the quarks. So, you know, the blue is larger than the green, essentially just because I chose it to be a stronger interaction strength. And then you can see two different versions that have a period of early confinement as either the dashed or the dotted line. You can see that there are different thresholds. That's because there are now mesons with a much wider variety of masses, and so there are different meson mass thresholds that you cross. And also that the cross section is much larger. And so this is really the key thing. By having the interaction of the dark matter freeze out during the time of confinement, the interactions are much stronger, and therefore I effectively get a much larger cross section. And that obviously is going to be very important when I try to match the relic abundance and ask what the parameters should be. This plot here in the upper right just shows you actually when the freeze out temperature takes place as a function of mass. It's not super exciting. You can see again, there's a big threshold at the top quark because the cross section jumps up a lot at the top quark mass. But more interesting here is down in the lower left, you can see the predicted relic abundance, again, for these two different values of the coupling or the two different colors. And for the solid curve is the normal QCD, and then the dotted and the dashed are the periods of early confinement. And what we see is that, of course, because the cross section is much larger, if we freeze out during early confinement, the relic abundance is actually much lower, right? Remember that the relic abundance goes like 1 over the cross section, roughly speaking. And so if we're aiming to get the amount of dark matter we observe today, which is this black line down here at 10 to the -1, you can see that actually we actually get that value for a much weaker interaction than we would have thought if we had had ordinary QCD, right? Ordinary QCD for this value, say the blue line, would have overproduced the dark matter by a factor of 1,000,000. But because of the enhancement of the cross-section during confinement, this actually corresponds, at least for around, say, 75 GeV dark matter mass, to just getting the right amount of dark matter exactly. And if we turn this now into a plot for the, so this is the parameter space of the coupling strength, right? So that's MS, remember larger values of MS or weaker couplings versus the mass of the dark matter at 0 temperature. We can also calculate what the cross-section for scattering at the xenon 1 ton experiment would be. Xenon excludes, right, the region of parameter space shaded in blue. It excludes small ms, which is stronger couplings. And you can see that actually for these interactions I've chosen, in the entire parameter space from 30 GeV to 400 GeV, xenon basically excluded all of it. They would have seen something already by now. But actually, if we have early confinement, we end up above, say, about 50 GeV or so with theories that are not constrained. And the reason for that, right, is that this enhancement of the cross-section is only active in the early universe during the early confinement. It ends at late times. And so while we're doing our experiments, we actually live with a small coupling, and that's what xenon effectively sees. The two different colors and of beta, just whether the mass shift is positive or negative, and because the sign of that is not actually specified by anything I've done so far, and it only affects this plot. If I'd chosen actually vector interactions, the situation would be very different. There's no large enhancement, and xenon 1 ton would still exclude everything. So this is something that is special to the fact that I chose a scalar interaction. So let me say something briefly about Axion production, and then I'll switch to talk about the LHC for a few slides. So Axion production through the misalignment mechanism, right, is again another way of trying to realize dark matter, in this case though for a very light pseudoscalar boson, and through a production mechanism that has nothing to do with thermal freeze out, but just basically depends on some initial condition of the universe. So what this plot is showing is the evolution of the universe as a function of temperature. So now temperature is dropping on the x-axis, so time is now going from left to right on this plot. What we're plotting is the density of axions as the black curve, and a few things to compare with. The standard axion production is the red dashed curve, And then, yeah, so let's just look at that. So the red dash curve, right, the axions, basically the density of axions grows as the axion mass is turning on. And then when we get to around the QCD scale, it sort of saturates, and it's more or less constant actually after that. So the standard picture for axion production, the rate at which axions are produced as a function of temperature looks something like this red dashed curve. In this theory with early confinement, what happens is the axion starts oscillating very early. It looks like matter right away, basically. So we get a huge density of axions, which then falls as we get towards the standard picture. When things go back to normal and we deconfine, the axions are actually depleted. All right, just because the axion energy density is completed. The number of axions is the same, but the mass suddenly jumps from a large value to a small value, right? And all of this is driven by the fact that the axion mass, right, is directly proportional to the QCD scale. And then the resulting amount of axions we get here is actually much smaller than we would have gotten in the standard picture, right? Despite the fact that it was much larger at early times. But at late times, it becomes much smaller when the mass plummets. And we actually end up with about 1,000 times less energy density in axions than the standard picture would have produced. So this obviously changes the usual connection between the axion decay constant, the initial misalignment angle, and the final density that we expect. So if we scan through the parameters of, say, lambda QCD versus the time of deconfinement, this plot shows you actually how much compared to the normal standard calculation of axion production you would expect to get. And you can see that you can sort of get up to the standard production. In other words, if the lambda QCD is happening early enough, if lambda QCD is close enough to the normal value and the deconfinement scale is happening large enough, basically nothing happens, the universe looks very normal, and you end up with the standard axion density calculation. However, if you go to cases where lambda QCD turns on very early at some large value and the deconfinement is late enough, you can get a big depletion of the amount of axions. In this parameter space we plotted, which is not really the limits of what's allowed, it's just indicative, you can get anywhere from, say, the full expected amount down to around 10 to the minus 4 or so. This little pink square actually corresponds to that cosmological history I showed you on the previous slide. And we have the same plot, but for two different values of the axion decay constant. But you can see that actually the values of the parameters at different points are different, but the trends are very similar because, of course, it's the same physics. So the net result is typically a suppression of the final density of axions. It allows us to have larger axion decay constants and still get the same amount of dark matter that we need. And that, of course, corresponds to lighter axions. And they can be naturally produced from order 1 misalignment with the correct abundance. And so it opens up regions of axion parameter space otherwise would have looked very fine-tuned. So I wanted to finish by, of course, connecting with the real subject of the conference and talk about the phenomenology of the singlet and how colliders can tell us about it. There are interesting parameters. You remember I had a picture where I used the Higgs vev to trigger the transition from confinement to deconfinement. I can actually, at any point in that parameter space, I can actually ask what the properties are. So for example, over here on benchmark 1, we have a QC confinement scale of around 90 GeV or so. It varies a little bit as I move through the parameter space. These B1 and B2, these are the cross terms between the singlet and the Higgs. And of course, they're very important for the phenomenology. At the same time, I can calculate things like what the mass of the singlet should be. That's these grayish. And you can see the mass of the singlet for this parameter benchmark are around 30 GeV or so. So the singlet is actually not that heavy. It's something the LHC has the energy to produce. In a second benchmark, you can see that, again, lambda QCD was sort of similar. It's around 80-ish GeV or so. Now the mass of the singlet is maybe around like 17, 15, 19, something like that. And these parameter spaces were motivated by explaining the baryon symmetry. So that's particularly what the blue and the red and the gray shaded are places where you don't generate the right baryon asymmetry. The white unshaded region is where you do actually produce the right baryon asymmetry. And so that's what's motivating these choices in this particular case. So the true hallmark of the dynamics I'm talking about is the presence of the scalar singlet field, and that's the thing that really we need to be able to try to detect. Now, it couples to gluons through the dimension 5 interaction that was characterized by M star, and that is the most fundamental and important property. So we definitely need to have that interaction. It also picks up Higgs interactions through mixing with the standard model Higgs, because the Higgs gets a VEV, and then those mixing terms, right, or on the previous slide, these B1 and B2, they cause there to be a mixing term between the singlet and the Higgs. And that means that it actually then looks like it gets a scaled down version of the Higgs interactions. But in this parameter space, the mixing is actually pretty small. It's less than about 10 to the minus 3 or so. And that's unfortunately too small for the LHC to have seen a deviation of the standard model like Higgs properties. It's actually small enough that even run 3 will be challenged to get that small. Maybe in very special channels, one could hope, but I'm not very optimistic about that. I think it's really going to depend on, how well those searches, how well the measurements of, say, standard model Higgs properties are going to get in the very, very clean channels. Yeah, 10 to the minus 3 is something that an E plus E minus collider can do with a large data set, but the LHC really has trouble getting there. And there could, of course, be additional dark decay modes. So what I plotted here is, and this is assuming that there are no dark decay modes, as a function of the mass of the singlet, this is the total decay width, or it's actually the partial decay width into various channels. You can see at the lowest masses, it can decay to GG. Right, remember that's the sort of the most fundamental thing that we're looking for is the coupling to gluons. Of course, as you go to higher masses, the fact that it mixes with the Higgs will allow it then, depending on the value of that mixing angle, to say decay into CC bar or tau plus tau minus, or even BB bar. And the masses that we're interested in don't quite get up to the top quark mass, so that would also be significant. If I turn these partial widths into the branching fractions, also, actually, if you look at the values of these widths, you can see that these decays are typically prompt. So, these things decay typically inside the LHC detector volume. The branching fractions, at the very lowest masses, it's 100% into gluons. But once actually the other channels turn on, especially if the mixing is not too small, and 10 to the minus 2 is right where maybe the LHC could actually see something, then you can actually get fairly equal fractions into gluons or into charm or bottom. Tau is always a little suppressed, but again, it could be appreciable enough that you could actually look for it. And the big challenge here is just that the mass is not very large, and so you're looking for a resonance in a fairly low invariant mass, which again has experimental challenges, but there I think there's something that maybe one could do. You can also produce the scalar off shell through gluon fusion. You can imagine that you have gluons, and since it's so low in mass, you don't produce it on shell, you just produce it off shell. But that actually it couples to WW dual effectively, so it could interact with. It could then lead to an anomalous production of, say, dibosons like 2Zs. Of course, usually it decays to dijets, and that I haven't even tried to look at because I think it's got very large backgrounds. But the diboson signal is something that's more interesting, and it was actually looked at by these authors, not in the particular context here, but just in a generic theory, but these limits apply to us as well. So this is a plot actually from their paper, and for very, very low masses, much lower than I'm interested in, there are bounds from supernova and from other things. But as you get to higher masses, the only bounds that are really active are these off-shell production ones, and they do actually a pretty reasonable job of cutting a chunk out of the parameter space. Now, the place where and this is, I believe, supposed to be an existing bound that they derived based on the diboson rates at 13 TeV. The parameter space I'm interested in had a slightly smaller value of the coupling to ZZ, and again, that's because of that small mixing with the Higgs. It's more like sort of an order of magnitude below where these bounds reach, but it looks like it is hopeful that something like run 3 could actually extend these bounds downwards and start to touch this parameter space. So I'm actually hopeful that there is some opportunity at run 3 of the LHC here. And if I look at things like a future collider, like say E plus and minus, I can then look for things like producing the scalar and seeing it decay at the BB bar. So that this was studied actually in this reference. And the actual lines here for the projections were taken from this reference, that we made the plot. So this is a mass of the singlet on the x-axis. And the thing on the y-axis is sine squared theta. So that's the mixing of the Higgs squared, and then times the branching ratio into BB bar, which turns out to scale out the signal that we're looking for here. And you can see that there are bounds from Opal and LEP that are relatively modest. A Higgs factory can actually do much better, like an order of magnitude better, and a Z factory can do an amazing job. These blue dots are actually all parameter scans that we had where we got the right baryon density. We couldn't really scan the parameter space well enough to be sure that we got all the points that work. But I think it's fair to say that, you know, you can get points sort of up here around the 10 to the minus 4 or so. So a Z factory could definitely probe an interesting region of parameter space. And my guess is if one did a careful scan, one would find that the Higgs factory is saying something too. We just didn't have the computing resources to take care of that, you know. And honestly, it's a crazy theory of BSM physics. I'm not sure it's worth spending the time on it. But it is important to note that you can actually say very interesting things about early cosmology using future colliders like this that go beyond even things like just say, hopefully producing dark matter at them. Okay, so to finish up, the idea that QCD may have undergone a period of confinement in the early universe is an interesting question. It highlights our general ignorance of the universe at times before BBN. It's worth exploring as part of a general investigation into the possibility that physics may hold surprises at high temperatures of the early universe. And I highlighted a few applications you could imagine, like the baryon asymmetry, rescuing WIMP dark matter, Axion production, that are otherwise, you know, in some cases ruled out by direct searches. I see this as part of a larger program that we should strive to understand the space of what is possible in the early universe, how to constrain the space of possibilities, and how to explore how they could cause us to rethink the standard solutions to its mysteries. And it also highlights that our high energy colliders are now entering a phase where they are really telling us something about the space of possibilities of the early universe. So with that, I'm going to say grazie.
Thank you, Tim. Thank you very much for the interesting talk. So we have time for questions or comments. So yes, Gennaro, please.
Yes. So maybe, I mean, if you could comment about top quarks. So, I mean, for concerning the DLHC phenomenology, you didn't mention decays of this singlet into TT bar pairs. Is it because you expect a too big background to be visible? And also another.
No, actually,
yes.
Sorry, it's really just because you know, this parameter space that was motivated by baryogenesis like to have lighter masses. But actually, the top quark signatures are interesting because, I mean, of course, you know, baryogenesis was just one thing I could imagine doing with this. If I did this for dark matter annihilation, I could have much larger masses, and you could imagine TT bar pairs. That actually is interesting. You might imagine seeing something, right? Because you can go glue to scalar singlet and then singlet into TT bar. You can imagine that there's a peak that would be visible. You know, imagine the scalar is very heavy. There could be a second, like sort of Higgs-like signal that is maybe at a TV or something. Also, even if the mass of the scalar is too small to be produced for it to decay into top quarks, it could still be produced by being radiated off of top quarks. And so you could also imagine something like a TT bar, again, Higgs-like signal, but now for a smaller Higgs mass. And actually, those are interesting things that we just didn't actually think about, but now talking to you is making me think about them.
Regarding top flavored hadrons, does your model predict any visible, top flavor meson or baryon, or we still haven't any chance to see it?
Yeah, it does, but the problem is they only exist in the early universe, so we can't see them today because today QCD is normal again. But yeah, the sort of the cute thing is that in this theory, in the early universe, all of the interesting things were top flavored mesons, and they had a big effect on the Higgs as a result.
Okay, thanks for answering.
Thanks for the question.
I also have a curiosity. I mean, as far as I understand, there is no hope that LHC can give some experimental hints on both for production or from precise measurement, and neither future hadron colliders, right? So my question is, if this is a property of all these kind of models, to escape from experimental detection from hadron colliders, or such property is something related to this extreme version of these models?
Yeah, that's a good question. So I think there are some hope maybe using this off-shell production channel, so that might work. In some sense, the problem is that when we did the phenomenology, we really focused on the region that would explain the baryon asymmetry. And I think there it's very challenging, largely just because of the small masses actually, right? The problem is you have couplings to gluons. So in general, hadron colliders are the right place to look for this. But the problem is that when you make a mass scale down around 10 GeV or so, the LHC just struggles because all of the selection cuts make it a challenge to analyze. But of course, that doesn't mean that it's impossible. It just means that it's more difficult, and the standard analyses don't necessarily apply. One thing I realized actually by answering Gennara's question is that if I actually don't look at the parameter space motivated by baryogenesis, but maybe look at the parameter space maybe more motivated by dark matter, I have larger masses, and in general, the LHC will say much more about it. So in some sense, I've given you a little bit of a skewed picture that was because I focused on the baryogenesis region, and really it would be worthwhile to focus on other regions too. I probably should have been more generic when I actually did the phenomenology.
Okay, thank you. So I don't see any other question from the audience.
Yeah. No, can you hear me?
Francesco, please. Yes.
Yes. Hi, Tim.
Ciao, Francesco.
Ciao. I wanted to ask you if, about the intensity frontier. No, for example, proposed experiments like SHIP, for example. Do you think that there is room there for detection of such kind of scalar?
I mean, there might be for very low masses. So in general, the coupling to gluons that we're interested in is large enough that the decays are prompt, at least if the mass is GeV scale. So the GeV scale particles probably, they decay too fast for SHIP to see them. They decay in Atlas, not in SHIP. But if I went to lower masses, which again, is a parameter space that's interesting, my attitude is that I should probably be agnostic and I should just look at all the parameter space and ask what I can do. There is a parameter space definitely in lower masses for which something like SHIP is relevant. And the decays become interesting because, of course, if you couple the gluons, once you go below lambda QCD, then you have to turn that into a coupling to pions. And so, there's some theoretical interest as well as to what the rate exactly is. And I haven't done the exercise, but it's a good question. And again, one that I probably should have thought about now that I'm hearing it.
Well, if you are still not done the exercise, then I would suggest even another exercise because now because there is this novel sort of campaign of observing neutrinos at the LHC with phaser nu and SND.
Yes. So, yes.
So okay.
As you might imagine at UC Irvine, I know a lot about phaser.
yeah, of course. So I don't know. That's probably another place where enlarging parameter space you may try and make the exercise.
No, that's right, actually, and because this is a case where you could imagine having a particle that is long-lived but has essentially what looks like more type hadronic signatures, which is not the typical thing that either SHIP or phaser is focused at. They tend to focus more at leptonic things just because they're looking at light particles. So, but yeah, actually, I should definitely look at this. Thank you.
Okay, so if there are no other comments or questions, we can thank Tim again. Thank you very much, and all the speakers of today.